This is the Part 3 video podcast for Chapter 7 on impacts of urbanization on hydrology. And I know that the Chapter 7 video podcasts are relatively long, but I want to alert you that the Chapter 8 video podcasts and Chapter 9 video podcasts are shorter, so that will make up for it. And the reason why these are so long, of course, is because there's so many impacts of urbanization on hydrology and associated processes. And so here in Part 3, I want to talk about impacts on water quality and ecosystem scale impacts. Well, there's three significant impacts on water quality that I want to talk about. The first is the discharge of toxic metals and organic compounds, and these can do a process that we call bioaccumulation up the food chain. So this involves the process in which small organisms are receiving these toxics, taking them up, but then larger organisms that eat those are grazing and getting all that, and then preferentially inside them, that material is stored like in muscle mass or in fatty tissues, and so it stays and doesn't get excreted out. And so then individually you're receiving a disproportionately high concentration. And then as you go up the food chain, the next level, then that continues to occur with that preferential retaining of those high toxic levels. The second thing is increases in populations of waterborne bacteria and viruses. So, when pigs and cows and sheep and everything, when their feces get into water, and remember that under industrialized agriculture, you have very high concentrations and storage of feces, then that can take place outside of an urban area, but can affect the water supply for an urban area or the river for an urban area, and then that can lead to massive illnesses where 100,000 people might get sick, and people whose immune systems are already compromised, on the order of a few hundred people, might end up dying. And then finally, nutrient loads and how that affects. So this is where the use of nutrients both in agriculture and municipalities, especially in suburban sprawl, can lead to downstream impacts on waterways, estuaries, and the coastal zone. Industrial pollution largely exists as what we call a point source. A point source is when you have a relatively large industrial facility or municipal facility putting out a very highly concentrated toxic waste. It might be nutrients, it might be toxic organic metals, and the idea is that the water body is going to dilute that. But in fact, in many cases that just simply can't happen. And the indicator of this, of how bad it got, was the Cuyahoga River fire of 1969, when the river literally just caught on fire because it was so badly polluted. In an urban context, there are a variety of sources of pollution. Most of these are not highly concentrated in the sense of a large industrial complex, but are concentrated at a very small point scale. And so we tend to think of these as more non-point sources because they're relatively diffuse. For example, vehicle exhaust, wear of tires and brakes, so there's particles dropping on the roads, spill of oil and other fluids leaking onto the road surface, getting into the drainage system, all of the trees and grass clippings that are left out on the street or fall and create a lot of debris and organic matter wouldn't be so much in and of itself, except that we use fertilizers, possibly even pesticides and herbicides, to promote the growth of urban-friendly plants. And so then we can get disproportionately more productivity than would be happening in the absence of that artificial process. We might have septic systems or breaks and sewage lines that can accumulate lots of waste, and then de-icing compounds and other kinds of things. So there's a lot of things that are happening, toxicity, nutrients, compounds that require oxygen demand in terms of breaking them down, like organic pollutants, bacteria or virus pathogens, and then sediments. A good case study to think of for the consequences of non-point source pollution over a vast urbanizing region is the Chesapeake Bay Watershed. This is the area that drains New York, Pennsylvania, Delaware, Maryland, Virginia, and the District of Columbia. So it's a very large region of the eastern United States. If we look at the nutrients that are produced from different kinds of land surfaces, forest, urban, suburban, pasture, and cropland, all of these human land uses trump productivity by forests in terms of nitrogen and phosphorus, but not necessarily in terms of sediment production. Well, no, I take that back. They are higher there too. And I showed in the Part 2 podcast how urbanization can yield very high intense spikes over a relatively short period, but agriculture, by being over vast land extent, can see massive amounts of erosion. And there actually was a book, I think it was called something like Erosion of Civilization. It was called Dirt, Erosion of Civilization, about how so much of the wealth of the world is tied up in having arable soils and how those are being eroded away as a result of human development of agriculture. So you can see the significant amount of production of material, nutrients, and sediment. Now, why is sediment a problem? Of course, sediment is natural, as are the others. It's just the large abundance of that material and the way it snuffs out downstream habitats, especially in aquatic zones. When I was doing my PhD on Chesapeake Bay, I came across this amazing plot. This was just some field data that was collected. Forget about the dots. I think that's just from the quality of the paper, and focus on the line. So here, this shows beginning April 3rd, 1996, and going to May 1st, 1996. And on the y-axis is the concentration of nitrate in Plum Tree Run, which is a creek in Maryland. For reference, the EPA standard is 10 milligrams per liter as the drinking water standard. Obviously, you're not going to want to drink most rivers anyway, but if you look at these concentrations, you're seeing that during this spring runoff period, upwards of 1,200 to 1,300 milligrams per liter, and sustained concentrations of greater than 400 milligrams per liter, for weeks along. So this is just one small, tributary, showing the effect of suburban sprawl and generating massive quantities of nutrients. Now let's look at a really remarkable watershed. This is the Anacostia River Basin, which drains to Washington, D.C. So Washington, D.C. is at the junction of the larger Potomac River and the smaller Anacostia River. The Anacostia River, if we look at its land use breakdown, is 76% developed. Compare that to the San Lorenzo case that I showed you in the Part 2 podcast. There's 20% forest, and so almost no agriculture taking place here. So if we look at what's going on in this watershed first, here's something you've probably never seen before, a trash map. So people walked up and down the streams, and the areas shown in red here are places where there's more than 50 pieces of trash per 100 linear feet of channel. So substantial amounts of trash. Volunteers removed 536 tons of trash during cleanups in the early 2000s, including over 11,000 tires. So this illustrates that one of the water quality and ecosystem effects of urbanization is just the massive dumping of what we could just call human detritus, just all the stuff, like people who don't want to pay the dump, they just dump toxic waste and all kinds of stuff just right into the waterways. This is a metric of essentially poop in the river, geometric mean of fecal coliform. So that's fecal coliform is associated with human feces. And what you can see here are these amounts, first shown in the Anacostia River from upstream to downstream, and then the Anacostia River connects to the Potomac River, so we can see the Potomac River at the mouth of Rock Creek and at Memorial Bridge. So as you go downstream, there's definitely a strong dilution effect. The swimming standard is 200, and so you can see that in the Anacostia River itself, well exceeding that. It's okay to be boating there because that's 1,000, but still, there is a very high risk of getting sick just by boating in the river. And certainly if you were to swim in the river, you would very likely get sick. Farther downstream, the dilution effect does take hold, and so it's not as bad. This shows during late spring runoff and summer rainfalls how the dissolved oxygen levels change. So dissolved oxygen is a constituent in the water. So water is made up of H2O, but intermixed among those molecules are molecules of just O2. So there's actually dissolved oxygen in the water, and not just the oxygen that structurally makes up the water. So dissolved oxygen is used by microorganisms to respire, to take in organic matter and break it down. And so when you have excess organic matter and nutrients, then microorganisms need to break that down. And that the more pollution there is, then the more dissolved oxygen has to be used to break that down. So you can see here that we're fluctuating here with these red diamonds where we're in the range of 3 to 5 milligrams per liter. It takes 5 to 6 is usually required for growth of activity. And actually, just if it was equilibrated with the atmosphere, it'd be more like 8 milligrams per liter. You can see that 1 to 2 milligrams per liter dissolved oxygen will not support fish. And below 3 is stressful for fish. So you can see that there's a period here of about a week where it's below that level, and then again later in June. And it tends to be that when you get these storms that the levels then drop. It's not always that way, but the reason that's happening is that the storms pick up all the material off the land and in the channels, and they flush it out to the larger channels, and then there's a strong biological oxygen demand in order to break down all that pollution. If we look at pollution in terms of toxic metals and toxic organic compounds, we can look at what's actually in organisms like fish as well as what's in the sediment on the bed of the river. If we look at the fish, we can compare the observed values in the first column to the EPA standards in the second column. And I've just did some color coding to try to give you a sense of what kind of danger levels we're talking about. So we look at some pretty nasty stuff. I mean, chloridane, DDT, dieldrin, I don't even know that one, but if you look, yellow is where we are a factor of 2 to 3 larger than the EPA value. Orange, we're 10 times the value, and red, we're like 100 to 1,000 times the value with aromatic hydrocarbons and PCBs. So these are some really nasty stuff, and you're seeing that the fish are heavily polluted, far beyond what the standards would call for. Now, sediment, if it just sits on the bed, it doesn't create any problems. But there's a lot of organisms that are feed on that material, and you could think of something like potentially oysters and mussels, potentially barnacles. There are also fish that will feed off of material on the sediment, and so then they can pick that up. And then also this can become dissolved into solution and become in the water as well. And so we can see copper, lead, and zinc being about 10 times what was present, or 10 to 100 times. And then here, thousands of times concentrations of these other organic compounds. So significantly polluted beyond standard. This is a pretty daunting set of numbers here. The amount of oil and grease flowing down the river in pounds per day. If we look at stormwater sources, so this is during high flows, 370 pounds of oil and grease flowing down the river per day. CSO is combined sewer outfalls, so these are where sewers are carrying the water that's both from when you flush the toilet, and so all that would normally go into wastewater treatment plants, as well as what's coming off of streets. That's why it's combined. More and more cities are separating those waste streams because if you have too much water running to the wastewater treatment plant, it can't handle it, and then it overflows. And so combined, we have a total of 1,000 pounds per day of water going down the Anacostia River. This now shows going to the scale of the entire Chesapeake Bay. So there have been significant efforts in Chesapeake Bay to try to abate the problems of urbanization. And if we look here at phosphorus, from 1985 to 2000, there was a significant benefit here of a reduction in municipal sources of this waste. So this is where, every time you flush a toilet, how much cities will treat that just depends on the technologies that they're using. And significant technological developments happened in the 70s and 80s, going from primary treatment to secondary treatment to what we can now call tertiary treatment. I believe tertiary treatment removes 95% of the nitrogen that's present in waste. And so you can see that by spending a lot of money, they're able to cut that about in half. However, since about 1995, it's pretty much leveled off. And the reason for that is that even if you decrease the amount of waste produced per individual, the fact that urbanization is driven by ever-increasing populations means that per capita use gets overwhelmed by the total number of people. And so you can see the projections here of an increase there, because as population increases, unless some new dramatic technology comes along to go to fourth order treatment or something like that, you just can't fight against population. Notice that industrial sources are steady. That's just a sign that technology has been highly mature. In the Chesapeake Bay, they set a standard in 1985 to try to reduce the levels of nitrogen, phosphorus, and sediment. The levels of reduction were different for each one of these, and this shows how well they've gone into achieving the goal. So on the x-axis is time, on the y-axis is percent of goal achieved, and this is showing a little bit older data, but what you can see is that there have been benefits like from 1995 to 2000, but then it pretty much just started to plateau and we don't see more benefits. So achieved about 40% of the goal for nitrogen, 60% of the goal for phosphorus, and about half the goal for sediment. So it is impressive. I mean, you got to give credit where credit's due. Like, society has reduced the amount of these contaminants that they have been producing, but they have not achieved the goals that they set, that they scientifically believe are necessary in order to save Chesapeake Bay. Oops. When you look at the bay, has there actually been a benefit? Okay, like have these reductions, have all the hardships or so, if you think about it, that we've instituted on ourselves, has that helped? And so this is a somewhat complicated graph, but let's just look at the tops of the bars. So the top of the bar shows the volume of water in all of Chesapeake Bay that's below 5 milligrams per liter. Remember, I showed you that below 5 would be stressful. It begins the problem where you have stresses on fish. So what you can see is that from 1985 to 2001, there are fluctuations from year to year, but there's been no systematic trend where what you'd like to see is a decrease in this volume of water. Now let's look at the colors. The colors indicate the different levels of severity of the problem. The solid red is the worst case, like essentially no oxygen in the water. And you can see that from 1985 to 2001, again, no trend at all. The area, the part of the bar that is either like red hatching or red polka dots, the same thing. It's the severe hypoxia, 0.2 to less than 2 milligrams per liter, and that fluctuates as well. So overall, what we're seeing is that even though civilization has decreased its contribution of these contaminants, the system itself has either not felt the benefit of that, like nitrogen might take hundreds of years to move through the groundwater system for that change in policy and human behavior to affect Chesapeake Bay. And so there's just no immediate gratification, and it also could be that they just haven't done enough. So we can see the will of the people to change, but in the end, they haven't changed enough to make a difference. Okay, let's look at the effects of urbanization on a few ecosystem scale indicators. If we could compare healthy habitats on the left to unhealthy on the right. Now, why does sediment matter? Well, sediment matters because in a healthy state, much of what happens in an aquatic system occurs on the bottom. You have all kinds of grasses, oysters, crabs, and so forth, everything on the bottom. And the reason for that is because the light goes right through, and although light diminishes, like estuaries tend to be relatively shallow, and so there's plenty of light that gets to the bottom, and so you have a bottom-dominated, or what we could call a benthic community. However, When you have an abundance of sediment in the water, then the light gets abated, and so everything on the bottom dies. And the only thing that can live is in the water column. And then when you throw in all those excess of nitrogen and phosphorus, you now get massive blooms of plant material because those plants are growing facilitated by the excessive nutrients. But then as they die, it takes a lot of oxygen for the microorganisms to respire and break down all that excess plant material. And so then that depletes oxygen and creates what we call eutrophication. When we look at the physical nature of the habitat, this is something I already commented on, we remove all of the riparian quarters that are here, we remove the complexity of the landscape, and we create small islands of habitat, but then these get heavily used by people, dog parks, people areas, and so as a result of that, there really isn't a lot of just naturally, quiet, like left alone habitats. Here's an interesting statistic that riparian zone is only 7% of the land area, but 70 to 80% of vertebrates depend on it. So overall, we have a degradation both in terms of physical abundance and quality of habitat, and also chemical quality and abundance of habitat. Another thing that you see here in the Chesapeake Bay, in the San Francisco Bay region, is the loss of the coastal zone. So I think more than 30% of San Francisco Bay has been filled in, and then a lot of urbanization that's take place on that fill or just land use. Tidal wetlands in California, as I'll show in the next unit on wetlands, has been reduced by 91%. So in coastal regions, cities are built on wetlands, and we fill in the estuaries. Here's a variety of other consequences that take place and what causes them. So on the top are different kinds of human policies and land uses, like impounding water, channelizing rivers, grazing, silviculture, all the way to irrigation. And hydropeaking is when you run a dam to release large amounts of water for a short period of time for power production, and then you just turn the water off altogether to then hold back water when you don't need any power production. And then X indicates a dominant influence, and O a lesser but significant influence. And so how do these things affect the environment? They can affect sediment yield, water yield, and so on down the line. So it just shows how the physical system and water quality change in response to different effects. And I'll let you look through that on your own. Okay, we can also put the effects in terms of a flow diagram. So we could start with increase and in abundance and diversity of pollutants. We could have an increase in speed of storm runoff, increase in volume of runoff, decrease in groundwater recharge. So this is like the hydrological impacts beginning at the top, like what urbanization does, and then how that goes to all the things we've talked about, like reduced groundwater, changes to river morphology, bank changes, vegetation changes, how that filters all the way through and then ultimately leads to the degraded natural resource. So that's it for Chapter 7. I know this was a long chapter, but the other ones will be shorter.